Everyone, and welcome to today's session on Introduction to PD on Power Transformer. My name is Sanjay Yadav, and I'll be hosting this session today. Speaker for today's session is Mr. Stefan Sibel, who is a service engineer Power Diagnostic Service at Mega Germany. Also on the panelists, we have Mr. Hussein Al Zuferi and Mr. Morad Hamdi at Mega Middle East, who will assist for the Q&A session. So before handing mic over to Mr. Stefan, I would like to highlight a few points. You all are being muted to avoid any disturbance during the presentation. Do park any question you may have for the Q&A session at the end or share it in the Q&A chat window. All questions will be answered at the end of the session. So participants has to ask the questions in the Q&A chat window. We have a Mega Middle East page on Facebook and LinkedIn. I will just share that in the chat section. So you can go on this link and follow us for regular updates. We also have upcoming webinars. I've shared that in the chat section. You can go on the link and register yourself for the upcoming webinars. There will be a small survey form at the end of the webinar, so please do fill the same for the feedback regarding the webinar. The recording will be sent to you within a week through the WebEx system and also the presentation. I now hand over the control to Mr. Stefan. So let's get started. Over to you, Stefan.
Before my colleague Stefan starts the presentation, for a few seconds, I wanted to make a few comments that this webinar is continuation of series of webinars related to partial discharge testing. We have already done a couple of webinars on partial discharge in the past, and we will have several scheduled in the future. So I'll suggest and recommend you to go to our website and stay tuned. So in today's webinar, my colleague Stefan first will present various methods and techniques on partial discharge on power transformers, so that would be very good to start to understand the concept, followed by a practical demo. So thank you all for tuning, and Stefan, you can start.
Yes, thank you, Mohammed, for the introduction. So I will now start with the presentation. So this webinar is about introduction on partial discharge measurements on power transformers. My name is Stefan Seibel. I'm from Germany. I work for Power Diagnostics as a service engineer. I do on-site measurements on power transformers on a regular basis with our mobile AC test system, as well as with portable equipment. And in the next few days, I will be working for a customer to install a monitoring system. So I am all in the monitoring and partial discharge measurement world. So today's webinar is based on the following topics. So first of all, I will give you a small introduction into the driving forces for PD measurements. Then I will do a little bit of theoretical background and showing you the root causes of partial discharges here on transformers. I will show a few standards and definitions. I will show a quick technical implementation for PD measurements on power transformers, and then I will give a live demo here from our laboratory. So let's start with the driving forces. So typically, special events force responsible parties to improve their risk mitigation program, and the higher the cost of an outage is, the stronger the pressure on this is on decision makers. So you need to know exactly what's going on in your component and improve planning of maintenance intervals, and select grid modernization if and when proactive, and make sure that you extend the in-service time by assessing the quality of your asset. therefore checking what is the current condition. So that's why PD measurements are important, because you have very expensive components. Transformers are super expensive, and if there is a failure or an outage, you will lose a lot of time and money, and therefore regular assessment of transformers are very important. Also, when we look at the norms, we know that power and distribution transformers are a vital part of every distribution networks. Transformers are very complex structures, and therefore, especially after manufacturing the transformers, we have extensive factory acceptance test requirements. There are a lot of standards addressing factory acceptance testing of power and distribution transformers, and all of these need to be tested by partial discharge. So the standard for factory acceptance tests on power and distribution transformers are shown below. I think I will just skip this part because, well, these are the standards and we all should be familiar with them, knowing that testing of these transformers is a big part of the standards. But just to give you a quick overview, there are different types of transformers like power transformers, like oil transformers, dry type transformers, or DC transformers. And all of these have their own sections of PD testing. There is, when you look at the failure rates of transformers, there is a high percentage of failures related to insulation problems, and these all can be detected by PD measurements. Also, many bushings and windings problems can be detected by PD monitoring or regular measurement checkups. Early failures due to improper factory acceptance test, transportations, or on-site commissioning can be detected by PD measurements. Also, random failures caused by special stress, for example, with high load, lightning, or switching impulses or ambient conditions, they can be detected, as well as the end-of-life failures due to aging of insulation materials. So looking at either monitoring or regular checkups from a utility or operator perspective, if you look at your asset with the PD monitoring system or with the PD measurement system in general on a regular basis, you can reduce your life cycle costs by knowing that your asset is not in a risk of downtime or blackout. You can increase the availability and the operation time by extending service intervals. You have a cost reduction due to change from time-based maintenance to condition-based maintenance. There's a reduction of reinsurance fees. Post-failure events might also be one reason to install a monitoring system. You can also use a monitoring system to reduce the redundancy in the grid by not having a spare transformer there, because you know, okay, this one is good, I will keep it running. Also, monitoring system can be interesting if you have an unpredictable load system stress due to renewable energy feed-in, and it's also important because there might be long lead time for replacements. You know, transformers you cannot buy and have it delivered on site next week. From an OEM perspective, a monitoring system can be interesting to demonstrate the highest quality and long-term insulation system stability. You might want to give it or install one if you give your customer a warranty extension. You can mitigate the risk of failures during the warranty. You can also give your customer remote support and diagnostics. you add features or the value for the asset. Also, you can give service and maintenance contracts and offer an all-in-one solution from the factory till the end of life of a transformer. So all this was the introduction. But let's look at the root causes of partial discharges in the next section, so I can give you a little background information on PD and why it's important to measure it. So generally, root causes of partial discharges in transformers are related to inferior quality of insulation materials. They can be related to fundamental design related problems. Maybe there's incomplete or improper processing of the insulation. There can be assembling related problems, humidity in oil, or over time aging of the paper insulation. And you can see here in these pictures that there are different mechanisms that might damage, or these are just examples like you have here on the top right, surface discharge due to low quality in the paper insulation, or below in the center a pattern of discharge inside a cable connection where you can see the exact cable connection which was bent during manufacturing process, and then afterwards we saw this pattern here which would have led to catastrophic failure. So generally here also this picture here shows a surface PD on a damaged bushing, which could be detected very easily. So other root causes are inadequate vacuum stage prior to the impregnation of the oil of the paper. We may have insufficient drying of the active part before oil impregnation, which leads to water in the insulation. Sometimes we still have remaining conductive particles in the oil or increased water content. There may be missing electrical connections or loose electrical connections. For example, floating static shields. We may have poor contacting of tap leads towards an OLTC, or drops of the casing glue in areas with elevated electric fields. All of these mechanisms can cause partial discharges in the transformers and lead to a breakdown. So the impact of the partial discharges caused by the previously shown mechanisms can be depending on the nature of the PD and the location of the main tank or inside the main tank. So sometimes we have accelerated degradation of the insulation materials. There is often gassing related due to strong PD activity, which causes subsequent deterioration mechanisms. In some failure types, we have overheating due to hotspots with high energy PD, which weakens the whole system. PD is generally a root cause for a reduction in the life expectancy of the transformer. And the worst case scenario is always an unexpected breakdown. Like you can see on the photo, there is a flash over to the transformer tank wall. So let me just show you standards and definitions about PD measurements on transformers. Typically after installation, we have the type and the routine testing, which requires a variable high voltage frequency power source from a motor generator set with a step-up transformer or an inverter-based system. We do these tests in HV laboratory or on a test field or of a factory or in a repair shop or on site. Then we have on-site offline testing with a transformer energized from a mobile AC test system, which is typically done on site at a substation, power station, or wherever the transformer is. We can do on-site online measurements when the transformer is energized through the grid with or without load. And also you can do on-site online monitoring when the transformer is energized through the grid and you just have the PD measurement system installed on site. These measurements are all related to applicable standards, which you can see on the right-hand side, or by technical guidances. Okay. So what are the reasons or objectives for these tests? So for type and routine testing, which is the FAT, factory acceptance test, you want to have a quality control to find PD activity at an earliest stage, like after the transformer has been built. This is a pass or fail criteria according to the predefined PD acceptance levels, which are defined in the standards. Partial discharges at this point will be caused by the design, processing, assembly of the materials or any other root cause occurring at the manufacturer site. So then the next point that we have is on-site offline PD testing, which is a so-called site acceptance test. There we need to do a quality check to find PD activity ahead of the energization of the transformer. The PD here might be caused by transportation, assembly, oil processing mistake, or other root causes during commissioning or recommissioning after a repair. For on-site online PD measurements, typically the objective is to perform a temporary typically time scheduled or condition based measurement to take a snapshot of the installation condition and find severe problems causing high PD levels. This is typically done when you have a DGA monitor installed and that gives you high ratings of gases like acetylene or hydrogen, and then you want to know what's going on in your transformer, and you can start measuring PD online. And then the last point is online PD monitoring, which is a continuous 24/7 monitoring, which unveils incipient, changing, or intermittent PD activity at an early stage, often done in context of special load conditions and with further comparable measures such as DGA, capacity measurement, Tangens delta, temperature, or load. So let us show you the technical implementation of PD measurements on transformers. So first of all, let's look at the physical effects of partial discharge. A partial discharge activity always creates several effects like a light wave, heat, a pressure wave, chemical effects, a high frequency wave, and electrical signal. So there are several ways to detect the partial discharge activity. So the electrical way is to measure it with a conventional measuring method defined in the IEC standard with a narrowband, limited wideband, or wideband measurement. Also with HF or UHF measurement techniques. And then there are the non-electrical methods like acoustic detection, chemical detection like DGA, or optical detection, where you look at the light waves. So partial discharge is a breakdown of a small area of the overall insulation. So you don't have a complete breakdown, but just a partial breakdown. And each PD pulse generates different measurable electrical signals caused by a local displacement current pulse, also causing electromagnetic pulse and acoustic pulses. And these can all be measured by our systems. So you connect the power transformer to the instrument like this in a test room area. So on the right hand side, you will see the ICM system connected, which is our PD measurement system for FAT, for example. And this will be connected using quadrupoles to the test tabs of a power transformer. And the quadrupole itself is an RLC network, which creates two signals that need to be measured. One is a divided voltage signal. So you have a synchronization signal for the voltage. And the other one is the PD signal. If you don't have test tabs on your power transformer, like if you use it on a distribution transformer, which is the same as we will do in the demonstration that I will give you in a few minutes, you can connect the instrument using coupling capacitors. In this picture, we see the coupling capacitor type CC100B/V, which is a 100 kV coupling capacitor. And this is also connected via preamplifiers to our instrument. And here, for example, we have an ICM system with 4 parallel input channel, and we build up a remote control connection to our computer system with the ICM system software. So this is for measuring the partial discharge straight at the bushings, where we can create an electrical measurement signal. If we find PD, we might want to use additional decoupling methods for diagnostics PD testing. For example, we can also introduce high frequency current transformers, which are so-called HFCTs. We can install further coupling capacitors on smaller voltage bushings. We have UHF drain valve sensors or flange sensors, which can be installed on the drain valves or flanges. Then we have acoustic sensors, which can be used for PD fault location to locate or narrow down the exact position of the PD fault to a few centimeters. And then there's also a so-called disturbance antenna to pick up external noise signals and gate these signals out from your measurement. The PD measurement system also has to be calibrated. An offline calibration is mandatory for all further measurements. The calibration is, as always, only valid for one frequency, one bandwidth, and the one measurement pass. There might be resonances affecting the calibration, and there's no calibration on UHF or acoustic signals because the calibration is always intended to be in picocoulombs or nanocoulombs. So a charge signal is not a UHF signal, and therefore you can do some kind of, let's say, sensitivity check on UHF or acoustic signals, but this is not a calibration. If you do a calibration online, you select the best suited measurement frequency where you have the best signal to noise ratio. and then you're good to measure. So how do we see the partial discharge in the measurement system? So there are different ways to visualize them. The easiest way is the simple meter display, which gives the apparent charge in picocoulombs. Then we have a scope view, which offers additional but very limited research capabilities. And the most advanced is the phase resolved PD pattern, the so-called PRPD, for an in-depth interpretation where you record the PD activity over a certain period of time, and then you can interpret the results here. So you look at the PD pattern, and different types of failures give different patterns, which I will show also in the demo. So every type of PD fault or PD activity gives a characteristic pattern which might change with activity, strength, and discharge activity. And by looking at the typical patterns, you can distinguish between PD faults. So let's go to the live demo. Two more slides. So first of all, I would like to show you the setup. We have a small distribution transformer here, which is a 20 kV to 400 volts transformer. On this transformer, we have installed 3 coupling capacitors to measure on 1U, 1V, and 1W. We can decouple the PD signals there. We have a preamplifier on every channel, which is this small box here. And then we have 3 HV filters connected to filter the PD signals from every phase against the other phase, because the connection here is an applied voltage test, so all HV windings are on the same potential, but to not to cross couple from one phase to the other, I did not connect them straight to each other, but I introduced a PD filter in between every phase so that we can see different activities on different phases as we would also have it in the reality. The low voltage winding is shorted and grounded, and on the ground cable I introduced a HFCT to also decouple PD signals from the ground side. So in this demonstration, I will show you a calibration of all phases in the M mode, as we will see it in the factory acceptance test. I will also do a sensitivity check on the HFCT in spectrum mode, so you can see how the spectrum calibration or sensitivity check looks like. We will do a so-called standard factory acceptance test measurement using the acceptance test panel of the ICM system. And well, spoiler alert, there will be some kind of PD fault, and I will show you a PD fault investigation or pattern interpretation on the results that we get. And in the next webinar in 2 weeks, I will also show the acoustic PD fault location, where we can narrow down the exact position of the PD fault. So,
Stefan, before we move to the live demo, can we have the question, please? We have a question asked, do we have any separate standard for auto transformer, or it will be the same standard?
I think it will be the same standard.
Okay, and the second question, last question, how effective is PD measurement using UHF signal for 230 kV power transformer? And how effective is this method to detect possible PD deep in the winding?
HFCT can be connected to the start point. And there you typically have quite a good sensitivity, but it all depends on the noise that we have around. But we installed several PD monitoring systems using a HFCT in the star point and got some pretty good results there. And we also do this during online measurements. So it's quite a good way to detect PD, especially if you have a lot of corona noise going on.
Thank you, Stefan. However, the question talks about UHF, effectiveness of UHF using unpowered transformers, and whether can it detect PD deep in the winding. So I probably can answer this question. We know that UHF method using ultra high frequency up to 2 gigahertz, and by physics, as frequency goes higher, the range becomes smaller. So that means due to nature of the winding of the transformer, where it filters the high frequency signals and PDs. So using UHF method, the PD deep in the winding will not be able to be detected by UHF. Basically, using UHF, you can only detect nearby problems only. So, Stefan, you have additional comments regarding this?
Yeah, that is perfectly correct. So the UHF signals are somehow direction related. So if you have a PD source in between two windings and the sensor is behind the winding, you might be able to detect it, but there's also a certain chance that you will not detect it if the PD source is on the exact opposite position of the transformer, then there's also a certain chance that it will not be detected. But UHF can be very helpful to measure PD on transformers, especially if you don't have the possibility to install connections on the bushings, or if you cannot go on the test tabs, and also to get additional information on the PD location.
Okay, great. So yes, I think UHF can be helpful to detect PDs in specific areas of the transformer. However, in general, the best to start with bushing connection here, bushing coupling capacitor or bushing tab. This is the most recommended method. We have more questions. Let us start with the demo, and we'll answer the questions after the demo.
Okay, so yes, so this here is our transformer, which you have seen before. I think I need to share the other screen. Just change this view. I will now start sharing this screen here. And yes, you can now see the control software of the ICM system. I will now give you a quick introduction into the ICM system. This will just be a very basic approach, because I think, yeah. Okay, so in the ICM system, we have several screens. We are using here a 4-channel ICM system, so we have 4 different. Wait a second. I need to use the other screen. Oh, sorry. Yeah. Okay, so we have 4 different measurement channels on the ICM system, because this here is a 4-channel system. We can set up a lot of settings here. So this here is the single channel panel, which is for one channel. So if we switch in between different channels, we see the activity on one channel alone. If we want to compare different activities on different channels, we can also use the multi-channel panel, which is this one here. So you can see here in a small window the activity that was recorded on each channel and switch by it manually. And for acceptance testing of power transformers, we have here the so-called AT panel, which will show the meter display for each channel and record the PD activity over time, and give a true parallel acquisition of the PD measurement signal. So let's start with calibrating in single channel mode. So I will now switch to this to the view in the laboratory, and then I will now go and calibrate the first measurement channel. So I will use a standard charge calibrator type Cal1A. I set it to a predefined charge. So you should now be able to see me. And this here is the Cal1A. I've set it to 50 picocoulombs, and I will now connect it to the first channel of the measurement system. So the green and yellow connection goes to ground. The other one goes to the HV bushing, and we will leave the calibrator here. And now I go back to the software, and then you should be able to see the charge or the calibration signal on the transformer. So here we are now in channel 1. If I press start here, you can see down here, this here is the charge signal. And the amplitude during calibration should always be 50 to 90%. So maybe we increase the gain a little bit more. Perfect. So now here you can see this here is our 50 picocoulombs charge. And now this channel here is calibrated in single channel mode. If we go to the acceptance test panel, you can also see here we have 50 picocoulombs here on this charge meter. And we can calibrate a so-called cross-coupling matrix, which is important for diagnostic testings, because during diagnostic testing, you want to see not only the activity on the same phase, but you can see the cross-coupling of signals to other phases, and then you want to know how much signal can cross-couple from this phase to the other phase so that you can distinguish between different faults. So then we do the same on the next phase. So this was 1U, which is connected to channel 1. I will now connect it to 1V. And now you can see on 1U, there's no calibration signal anymore. So we go to channel number 2. And here we can see the 50 picocoulombs signal. Yeah. So the 50 picocoulombs are calibrated now. Then we go back to the acceptance test panel. We calibrate this channel here. And then we go to the next one. So calibrate 1W. Now it is connected to 1W. And you can see here in the AT panel that we have the signal now on 1W. So let's calibrate first in single channel mode. Yes, 50 picocoulombs. Might want to see a little bit of background noise, so we reduce the low level discriminator, but that's perfect. Then we calibrate the cross coupling matrix. And that's it. 1U, 1V, 1W. And now we call this channel 2N. Because on the neutral side, we have short-circuited the neutral side and installed the HFCT there. René, can you follow me real quickly? So you can see here, this here is the low voltage side, which is completely shorted and connected via this cable to the HFCT, which I will show you in a second. So I will just clamp on the calibrator here. And you can see the HFCT down there. I created a little loop.
Your camera is not visible because the ICM window is on top of it.
Oh, sorry, Mohammed. Yeah, I forgot to switch it. Okay, so you can see on the right-hand side the HFCT, which is also connected to a preamplifier. And then we show again the shorted neutral or the low voltage connection, which is this one here. So this here is the 400 kV side. It's just shorted and grounded via this cable. And here's the connection of the charge calibrator. Okay. So now I will go back to the software. Let's check out this the spectrum of this calibration impulse. So for this, I chose the spec mode. And in the so-called spectrum mode, you can see the frequency spectrum of the calibration signal. Yes, let's put this on maximum hold. And now you have different center frequencies, which you can choose to measure your PD signal in the so-called spec mode. So let's have a look here at the center frequency 1, which is at a band, which has a bandwidth of 300 kilohertz. Record this again. So I've set the bandwidth to 300 kilohertz. The center frequency is also 300 kilohertz here for CF1, which is recording this pattern here. And if I press start, you will see that we have a little bit of background noise and that we have a certain signal here, which you can see now in quite large. So if we call this 50 picocoulombs here and restart the acquisition, like you can see here, this here is 50 picocoulombs, and we have a background noise of about 4.88 picocoulombs. Then if we go back to the spectrum mode, you have seen here this high peak. So we move the center frequency 2 in the center of this peak, and we look at the CF2, which is the top right path. And we should be able to get a better signal to noise ratio there. Interesting. Ah, yeah. Forget what I showed before. So the pattern that we get as CF1 is now this one here. And you can see the calibration impulses down here. So whatever happened before was not correct. So this here is now 50 picocoulombs, and the noise level is about 36, maybe 40 picocoulombs. So here we have a very bad signal to noise ratio if you measure at this part. So you want to measure here in the top peak, which is in this case at 680 kilohertz. It can depend on your setup. It can depend on your HFCT type. But what's most important, you have a very bad signal to noise ratio in this section. You have a good signal to noise ratio in this part. So you want to measure here. And this is one way to do on-site measurements by choosing a good signal to noise ratio frequency. That's all I wanted to show you about this. So we always measure with CF1. So I will now, as you can see now, I moved CF1 to the resonance peak here. I will calibrate this now as 50 picocoulombs. We now have about 5 to 6 picocoulombs background noise, which is good. And then we go back to the AT panel, calibrate, and that's it. And now we are good to do a little demonstration. So René will get the calibrator out, and then we can start with the test.
Again,
So,
Stefan, if you can remove the window, the software window, will be good.
yeah, sorry. We just got the calibrator out, and we are now closing the test room so that we can start applying high voltage. So not much to be seen here. there's a transformer. But the interesting part starts now in the software. So when you do factory acceptance testing, you can set your trigger interval here, and then we can start the record. It will have a few predefined values here, but you can add your transformer ID, the condition ID, name, test department, and so on and so on. A lot of information into this. You can choose your directory. I'll just put this on the desktop, and I can call the file here test run mega Middle East. And then as soon as you start the OK button, it will start recording the measurement. So this is very handy for factory acceptance testing. And then you can start applying voltage and start your test run. So now let's just start with a little bit of voltage. You should now be able to see, maybe we go to this panel, the voltage level over time. So why is it not showing the voltage? Yeah, because of this. I forgot to reconfigure this. Okay, so we have here the record over time. Not much going on at this point. So we have like 2.2 kilovolts here on every channel. Of course, it's measuring the same potential. You can start recording a phase resolve partial discharge pattern, a so-called PRPD, on every channel. For example, this here is on channel 1, which is 1U. There's no activity at all. Same for channel 2. No activity. Channel 3, which is 1W. No activity. And then here on the neutral, well, of course, there's not 2.2 kilovolts on the neutral, but I use the sync 1 to synchronize the PD pattern on this channel. So yeah, that's it. And then when we further increase the voltage a little bit, we see there is something going on. Like maybe I can also adjust this scale here, let's say to 200 picocoulombs, so you can see a little bit more. So here is some kind of activity. We have like 35, 36 picocoulombs and like 6 picocoulombs on 1V. So let's have a look at this pattern here. Aha. So what is this? This here is in the negative half cycle of the voltage. We see a little bow-shaped discharge in the pattern, and that tells me that we have some kind of external corona noise here on 1U. So now we want to know what's going on 1V. And we also see here in the negative half cycle a little bit of the same activity, which is just cross-coupled via the winding. So let's further increase the voltage. We're now at 10.8 kilovolts. We can have a look at 1U again. What you can see now is that the bowl-shaped activity has now increased in width. So more phase angle, the phase angle has increased, which is typical for external corona noise with increasing voltage. So first of all, you have a very small window at low voltages, and the higher the voltage, the wider the phase position is where you have the activity. Then on 1V, we can also see the same activity again. Also here, the phase angle has increased because, of course, it's the exact same signal. 1W, which is the furthest from the activity, you can only see a little bit of the same signal. And on 2N, where we have the HFCT, yeah, we can also see a bit of the same activity here, but not very much. And if we then further increase a little bit more, we now start seeing something crazy. We still have the same activity here on 1U, and now we have further activity on 1V and 2N. So let's have a look at this one here because it was clear before. Yes. So now we have some very clear partial discharge pattern here. Let's look at 1U again. So on 1U, we mostly see the external activity. 1W. We see kind of both activities, but only very small amplitudes, which tells me that this is not the position of the fault. And then on 2N, we see quite high level of the internal activity. The shape of the pattern tells me that this is some kind of internal activity, and we also have the highest readings here. So the pattern interpretation of this activity here tells me that it is somehow closer to 2N and that it is somehow related to 1V. Yeah. Maybe we can reduce the gain here a little bit to maybe 4. And have a look at this pattern again. Yes. And you can use the mouse to point the crosshair to the highest activity, and you can read up here, this is like 110 picocoulombs. And sorry, I need to end this. Yes, and this here is the reading of 1V. So the pattern here shows a maximum amplitude of 53 picocoulombs. So the highest reading that we get is from the LV side. So my first interpretation of the results based on this measurement that we are doing here right now is that the PD activity is somehow related to 1V, and we have the strongest activity towards the low voltage side. Yes. And now I can reduce the voltage again. And what we should see now is we have PD exception, so no more PD activity of the internal activity. And the external activity is still active at what we have now as 5.6 kV. But you can also see the phase angle here is smaller again now. And if we further reduce the voltage to 0, then also this activity will die down, as you can see here. All right. So we can stop the record now. And once we have stopped the record, the software can automatically create a report file. Let's put it as a Word document. It will take some time to create this Word document, and this will hold all the information, which is the PD level during the measurement, the voltage and PD curve over time, and also the patterns that were recorded during the measurement. So while we are waiting, are there any related questions yet?
There are several questions. So while the report is being generated, I read some of them. One of them asking, what is the recommended bandwidth of calibration for calibration?
That will depend. If you, well, there are two possibilities to, it's blocked. There are two possibilities to measure. So one is measure in the amp path, and one is to measure in the spectrum path. If you measure in the spectrum path in a normal environment, I would recommend to use the 300 kilohertz bandwidth. If you measure in a laboratory, I would recommend to use the amp path, and then you should look at your background noise level and then choose which bandwidth you want to use. You can go from with a lower cutoff frequency with 40 to 40, 80, or 100 kilohertz, and with the upper bandwidth, upper frequency, you can go to 50, 600, or 800 kilohertz. So you have the possibility to measure either from, let's say, 100 to 250 kilohertz. So that's only 150 kilohertz bandwidth, but still IEC compliant. Or if you want to use the full range, you can go from 40 to 800 kilohertz, where you have the best detection possibility, but you also have a high susceptibility to noise. So what I often do when I'm on site, I measure from 100 to 600, or I just use the spectrum path and measure from 150 to 450. Which is always a very good compromise, especially when you use a frequency converter-based source.
Thank you, Stefan, for answering. We have one other person asking, 4 channels means 4 measurement of PD? Yes, it means measuring 4 measurement at the same time. In our case, we are measuring at each phase,
Yes.
primary side, so 3 phase, and HFCT on the neutral. So we are measuring at 4 locations.
Yes.
With four sensors. Another person is asking, tan delta test not enough to identify failure of installation? No, the answer is no. The tan delta test is different than partial discharge. To understand, tan delta generally gives overall condition of the installation. For example, deterioration of the oil, age of the oil, paper condition, overall, the whole paper in the transformer, the whole condition. It's like aging of the person. It's like saying how old you are. So this is tan delta. PD is like specific pain location in your body. If you have knee pain, it's different. You can have a knee pain, for example, or a specific location pain issue. That's a PD. So PD locates a problem in specific areas like floating particles, sharp points, bridges, fiber bridges in the oil, tracking discharge, voids, delamination. So localized issues in a specific location, that is PD. However, overall condition of this aging of the insulation, that's the tan delta. Okay, so anything more to add before I?
Yeah, maybe short introduction, or like we have here. This here was measurement channel 1, so this is 1U. The center one is 1V, and this one is 1W. So we have here channel 1, channel 2, and channel 3. And on the rear side, the shorted low voltage side was connected to our channel 4, which was the 2N. Okay, Mohammed.
Thank you. We have another person asking, what is the standard reference to choose the value of the picocoulomb on the calibrator? What is the effect? Is value too high, low on the measurement? So basically he asked, is there any standard or how to choose the calibration value on the calibrator?
Yeah, so typically the calibration should always be done in a range of what we expect during the measurement, or of what is allowed. So for example, on power transformers, you always have an acceptance level of 250 or sometimes 500 picocoulombs. So in these cases, I would calibrate with 200 or 500 picocoulombs. Nevertheless, it is often possible to have a very low background noise level. So if you can calibrate with, let's say, 100 picocoulombs, and you can still see a good signal to noise ratio, then I would recommend to calibrate with even lower values, because then it's possible to see even lower amounts of PD for during the measurement. Let's just show you the report that was created during this measurement. So here we have the report. We have the test time, test date, test time. Well, here in Germany, it's a bit earlier than in Middle East. Here, this is the name that I gave it, Test Run Mega Middle East. There were no remarks. Here we have the full values of the PD recorded. Well, I recorded every second, so we have a lot of values here. That's also the reason why it took so long to create the report. And then in the end, we have the strip chart that was recorded during the measurement. And what is also cool about the ICM system, which is a feature that I can also show you here, like you can copy paste. For example, here, if we have an interesting pattern here, maybe we have some here. So you can just press Control C to copy this pattern, and you press Control V, and you have the pattern right inside your report. This is something that I always do when I do measurements on site. So I do not only rely on the recording of the ICM system, but I also often copy and paste patterns that I just created. Okay. Any more questions?
Thank you, Stefan, for the demonstration and presentation. So I think we limit the questions to that level for now. If anybody else has additional questions, please do reach us at our email address. My colleague Hussein Al-Juferi will put his email address in the chat section, so you can reach him later on. You can also view this webinar again if you want to view it, the recording as well. Additionally, I would like to make a conclusion about some of the things my colleague mentioned. Again, reiterate that this measurement here is done via pushing tap sensor at the tap sensor, or it can be done at the via coupling capacitor, like done here in the setup, which you can use the IEC 61850 recommended range at low frequency range below 1 megahertz. This frequency range, which detects most of the problem throughout the power transformer. And additionally, using the UHF sensor, only local problem, nearby problem can only be detected. It cannot detect the problem deep in the winding. Also, my colleague shown you how useful is the spectrum analysis. This is something mostly not available in most of the equipment. So this is additional option in the equipment shown here, where with a spectrum option, you can see at which frequency range the signal is better and noise is less, and you can use that center frequency there. So you can select your center frequency and the bandwidth accordingly.
One thing, sorry to interrupt you, Mohammed. One thing I forgot to show you, of course, the external corona activity that we saw was created by this wire, which is only connected to phase 1U. Yeah, sorry for interrupting you.
No, great, thank you. And additionally, my colleague Stefan shown you the steps to locate the fault, approximate fault. In this, for example, here, there are several methods done to locate and find out where approximate fault in a power transformer. Since 4 sensors plus HFCT 4 sensors installed, plus the information regarding PRPD pattern, polarity of the PRPD, and the result of the PD strength at each phase, the approximate location can be detected on which phase, for example, and which area. This is what I've done today. However, the more precise location can be further enhanced by acoustic method, which we will do in next webinar. Again, thank you all very much for attending, and have a good day. My colleague Hussein Al-Jufari email in chat section. Any information, anything else you would like in future, please get in touch with him. Thank you very much and have a good day.
Thank you very much, everyone. Thank you.
Thank you for attending.